Today I am going to present what is the effect due to sinking of support and rotation of support on a fixed beam. You know, in simply supported beam, if one of the support settles, there is no effect on moment and shear in the beam. But in the case of fixed beam, if one of the support settles or rotates relatively to other, there are moments developed at supports. These moments induce shear force in the beams. Look at this figure. This is one fixed beam, and here this is the fixed end, and here this is the sinking of support. Here the B, this is A and B support. So here you see the B support sink by amount delta, and the new position is your B dash. B dash. This is the new position of the B, and this delta is the sinking of the end B to the B dash. And look at this figure. So here this end is your fixed, and this end is your rotate with respect to this end. And what is the rotation? Theta B. So you know that the rotation is your in anti-clockwise direction. This is the direction of the rotation. That is due to the sinking of support or due to the rotation of support. What is the moment developed at supports? That we'll find out here. So first we will discuss due to sinking of support. So due to sinking of support, what is the effect on the fixed beam? Consider a fixed beam AB of span L whose ends A and B are fixed at different levels. Let the support B sinks by delta with respect to A and take position B dash. Here this is, look at this figure. Here this is the fixed beam, and here this is the end A and this is the end B. So here the end B is settled by an amount delta. So that is, this is the original position, and after settlement, so this is the new position of the beam, B dash. Let the support B sink by delta with respect to A and takes a position to B dash. This is the new position, and this is the settlement amount delta. Let MA and MB be the fixing moment at the ends. MA and MB be the fixing moment at the ends. For this case, MA is negative and MB is positive. So here you have to take negative, this is, and here this is also anti-clockwise. Here you have to take MB is your positive. When you are considering this moment, so this is the bending moment diagram, and when you are considering this moment, and this is the bending moment diagram. Because when you are taking this moment itself, so what is the moment this side 0, and this side is your moment is your MB, and when you are considering only this moment, so due to this moment, what is the moment this side MA, and this side is your moment is your 0. This is the bending moment diagram when you are taking separately moment MA and MB. So this is the bending moment diagram. You know, on the moment area theorem, here you see when you will draw a tangent here, when you will draw a tangent at A, so that tangent will pass through the original axis of the beam. Here also at the position B dash, when you will draw a tangent here, and that will also parallel to the axis of the beam. So here what is the slope between the A and B? What is the rotation between A and B dash? So 0. So if the slope at A and B dash will 0, you know if the slope at A and B dash is your 0, from the moment area theorem, the total area of M by I diagram between A and B is your equal to the slope between A and B. But here the slope at A and B is your equal to 0. The slope at A and B dash is your equal to 0. So here you have to take the total area of M by I diagram between A and B is your equal to 0. You take what is the area of this M by I diagram, and you take what is the area of this M by I diagram. So here you have to take the total area of M by I diagram is your equal to 0. So what is the area of this diagram? Half into MA into L. Because the length of the beam is your L, and this ordinate is your MA. So half MA is your L. And what is the area of this one? Half into MB into L. So MA into L by 2 plus MB into L by 2 is very equal to 0. This is the area of M by I diagram is equal to 0. At the slope at A and B dash is equal to 0. So you have to take the area of M by I diagram is equal to 0. Thus the fixing moment at two support will be equal and opposite. So after simplification, you will get M is equal to minus MB. This is your equation 1. Then the deflection between two tangents drawn at A and B will be delta. You see here, when you will draw a tangent here, so this will pass through the axis of the beam. And when you draw a tangent here, this will also parallel to this axis. If you draw a perpendicular line at B, so that line will be meet to the tangent at B dash. And this deflection is your delta. So this is your equal to the moment of area of M by A diagram. From the moment area theorem, so you know the total moment of area of M by A diagram between A and B is equal to delta. So you find out delta is equal to, you have to take what is the moment of this area about this end and what is the moment of this area about this end. So what is the area this one? What is the area? Half into M into L. And what is the central distance from the end B? 2L by 3. Because this is your L. So from this end, so the central distance is equal to 2L by 3. So half MA into L into 2L by 3. This is plus what is the moment of this area about the end B? Half MB into L into L by 3. From this side, so what is the moment of this area? L by 3. MB into L by 2 into L by 3 divided by EI. So this is the M by I diagram. So E is equal to the deflection between A and B. What is the intercept here? This is the delta is equal to, so the moment of area of M by I diagram between A and B. So this is delta is equal to this one. Then after MA L square by 3 plus MB L square by 6 divided by EI is equal to minus delta. You take here minus delta because the downward deflection you take negative. Considering the downward deflection is your negative and upward deflection positive as per sign convention. So here you take, because this is downward deflection, so here you take this is your negative minus delta. Then MA L square by 3 plus MB L square by 6 is equal to minus EI delta. Then 2MA plus MB L square is equal to minus 6EI delta. 2MA plus MB is equal to minus 6EI delta by L square. This is equation 2. We know from equation 1, MA is equal to minus MB. So just to put this in equation 2, MA is equal to minus MB. So minus 2MB plus MB is equal to minus 6EI delta by L square. Then after simplification, this is minus MB is equal to minus 6EI delta by L square. Therefore, MB is equal to 6EI delta by L square. If MB is equal to 6EI delta by L square, then what is MA? MA is equal to minus MB. So MA is equal to minus 6EI delta by L square. So due to the sinking of support, this is the fixing moment produced at the end B, and this moment is induced at the other end MA. This is a minus 6EI delta by L square due to the sinking of support B. Here you see, when the ends of a fixed beam are at different levels, the fixing moment at each end is equal to 6EI delta by L square. This is the fixing moment. At the higher end, that is at A, this moment is hogging moment, negative. This is higher end means here, this is the higher end and this is lower end. So here, so the moment is your hogging moment, this is your negative. Already you got here, MA is equal to minus 6EI delta by L square and MB is equal to 6EI delta by L square. So at the higher end, that is at A, this moment is hogging moment, negative. At the lower end, that is at B, this moment is sagging moment, this is positive. So the moment at A is equal to minus 6EI delta by L square and moment at B is equal to 6EI delta by L square. So this is the fixing moment at the support A and B that is produced due to the sinking of support B by delta amount. Then coming to what is the effect of rotation of support. So here we will discuss due to rotation of support, what is the effect on a fixed beam. Consider a fixed beam of span L, here this one, and here this is the rotation takes place. The rotation takes place in anti-clockwise direction, the amount is theta b. And due to this rotation, what is the effect on a fixed end? What is the fixed moment produced at the end of a fixed beam? Due to this rotation theta b, what is the fixing moment produced at the fixed end A and B? We have to find out here. So this is the anti-clockwise rotation, and we will draw a tangent here. This tangent and the original axis of beam. So this is the rotation. So here the rotation takes place in anti-clockwise direction. This is your theta b. Let rotation at support B be theta b in anti-clockwise direction. The angle between the two tangents between A and B will be theta b. Because when we will draw a tangent here, so that will pass through the original axis of the beam. And when we draw a tangent at B, so this is the tangent. So what is the angle between the two tangents? What is theta b? So let rotation at support B be theta b in anti-clockwise direction. The angle between the two tangents between A and B will be theta b. Let MA and MB be the fixing moment at the two supports. We will find out these two moments due to the rotation of a support B. Due to rotation of a support B, what is the fixing moment developed at the end of the beam? Here you know, so this is the theta angle, because when you draw a tangent at A, so this will pass through the axis of the beam, that is passing through the point B. And when you draw another tangent at B, the angle between these two tangents is the theta b. So here you have to take the area of M by I diagram between A and B is equal to theta b. So theta b is equal to, you take the total area of these two diagrams. So what is the area of this diagram? Half MA into L. And what is the area of this diagram? Half MB into L. So MA into L by 2 plus MB into L by 2 divided by EI is equal to theta b. Then MA plus MB is equal to 2 EI theta b divided by L. This is equation 1. MA plus MB is equal to 2 EI theta b by L. So this is equation 1. Then what you have to take, because here you see this is the tangent, this tangent is passing through the original axis and through the point B, and this is another tangent. So this is also passing through the point B. So what is the intercept between these two tangents? 0. You know from the moment area theorem, the moment of area of M by I diagram between A and B is equal to the intercept between the two tangents. But here both the tangents are passing through the point B. So there is no intercept. So the intercept is equal to 0. So here you have to take the moment of area of M by I diagram between A and B about B is equal to 0. Total moment of area of M by I diagram is equal to 0. So you take what is the area of this one and moment of area about the point B. Half MA into L into 12 by 3. Half MA into L into 12 by 3. And what is the moment of this area? Half MB into L into L by 3. Half MB into L into L by 3 is equal to 0. Then after simplification, 2MA plus MP is equal to 0. So this is equation 2. Then simplifying equation 1 and 2. After simplification, we get here this is equation 1. MA plus MB is equal to 2 EI theta b by L. And here this is 2MA plus MB is equal to 0. Equation 2. Then after simplification of these two equations, so you will get minus MA is equal to 2 EI theta b by L, and MA is equal to minus 2 EI theta b by L. Then you know MB is equal to minus 2 MA. From the equation 2, you know MB is equal to minus 2 MA. But here you got MA is equal to minus 2 EI theta B by L. So MB is equal to 4 EI theta B by L. So here you got what is the moment produced at end A and at end B. The moment at end A to produce a rotation by theta B at B. So the moment required at B is equal to MB is equal to 4 EI theta B by L. The moment induced at A is equal to MA is equal to minus 2 EI theta B by L. So due to this rotation at B, theta B, so the moment produced at B is equal to 4 EI theta B by L, and the moment induced at A is equal to MA is equal to minus 2 EI theta B by L. Due to the rotation of support B by theta B amount, so this is the moment produced at the end B. That is MB is equal to 4 EI theta B by L, and this is the moment induced at the end A, MA is equal to minus 2 EI theta B by L. If a fixed beam AB carrying a load, the end B loses a little fixity and rotates by theta B amount. The end moment at B will be reduced by 4 EI theta B by L, whereas the moment at A will be increased by 2 EI theta B by L. So this is the moment that you can find out. MA is equal to minus 2 EI theta B by L, and MB is equal to 4 EI theta B by L. So due to the rotation of support B by an amount theta B. Then coming to one example, a beam AB of span 5 meters, fixed at both ends, carries a uniformly distributed load of 18 kilonewton by meter over the whole span. The right end sinks by 15 mm. This is right end. Determine the fixed end moments and the reaction at the supports. Draw SFD and PMD. Take E is equal to 200 kilonewton by mm square, and I is equal to 7.5 into 10 to the power 7 mm4. This is fixed beam. So here this is given the loading. W is equal to 18 kilonewton by meter, and the length of the fixed beam is your 5 meter, and this is the settlement takes place. Thus support B settled by an amount 15 mm to B dash. This is before settlement and this is after settlement B dash, and this is the settlement of the point B to B dash 15 mm. So what you have to do here? So here you have to find out what is the fixing moment or what is the fixed moment due to the UDL and due to the sinking of support. You have to find out what is the fixed moment due to uniform distributed load, and also due to the sinking of support. What is the fixed moments? That you have to find out. The MA and MB that you will find out due to UDL and also due to the sinking of support. Find out the fixed moment due to UDL and sinking of support. What are the steps? You have to take a simply supported condition, and you have to find out what is the free BMD or simply supported BMD, and you have to find out what is the bending moment, the maximum ordinate of the free BMD. Because here there is having the uniform distributed load, and due to this UDL and for simply supported condition, so what is the bending moment diagram? Parabolic, and what is the maximum ordinate? What is the maximum positive moment or sagging moment at the center? This is WL square by 8. The free bending moment diagram is parabola whose central ordinate is WL square by 8. So this is the load. This is the load 18, and this is the length. So 18 into 5 square by 8. So this is your equal to 56.25 kilonewton meter. So this is the maximum ordinate of the free bending moment diagram. But here you have to find out the fixed moments at the end. You have to find out the fixed moment at the end due to the UDL and due to the sinking of support. So first you find out due to the uniform distributed load, what is the piston moment at end A and at end B? Piston moments at end A and B due to loading is equal to minus WL square by 12. You know, this is the formula. When there is present the UDL throughout the span, and what is the piston moment at the end? Minus WL square by 12. Already we have discussed in previous class. So piston moment at the end A and B due to loading is equal to minus WL square by 12. So MA1 is equal to MB1 is equal to minus 18 into 5 square by 12 is equal to minus 37.5 kilonewton meter. So this is the moment at the end A and B due to the uniform distributed load. Similarly, find out what is the fixed moment at the end A due to sinking of support. So due to sinking of support, find out what is the piston moment at the end A and B. So first here you find out what is the piston moment at A due to sinking of support. So here you take MA2. Due to sinking of support, you take A2. MA2 is equal to minus 6EI delta by L square. MA2 is equal to minus, this is 6, EI is given, EI and delta is given. So E value is given 200 kilonewton by mm square, and I is given 7.5 into 10 to the power 7 mm4, and delta is given mm. So this is E and I. Kilonewton by mm square, this is mm4. So here you will get, after multiplying this E and I, so this is kilonewton mm square. 200 into 7.5 into 10 to the 7 kilonewton mm square. So just to convert this mm square to meter square, so take 10 to the power minus 6. This is, or divide by 10 to the power 6. And then here this is given in mm. The settlement 15. So here also you have to convert this to meter. 15 by 1000. 15 by 1000. So this is in meter. So then you will get the answer MA2 is equal to in the answer you will get in kilonewton meter. So MA2 is equal to minus 54 kilonewton meter. Similarly, find out what is the piston moment at B due to sinking of support. MB2. So MB2 is equal to plus 6EI delta by L square. MB2 is equal to plus 6EI delta by L square. Here you put the value of E, I and delta. So E is your this one, I is your this one, and delta is this one. So this is EI kilonewton mm square. So then you have to divide by 10 to the 6, and this is in millimeter. So you have to divide by 10 to the 3, then you will get in meter. So MB2 is equal to plus 54 kilonewton meter. So this is the MA2 and MB2 due to the sinking of support B by an amount 15 mm. Then you have to find out what is the total moment at A and what is the total moment at B. You have to find out what is the total piston moment at A, and you have to find out what is the total piston moment at B. The total piston moment at A is equal to the piston moment due to the UDL plus piston moment due to the sinking of support. So MA is equal to MA1 plus MA2. So due to UDL you got here minus 37.5, and due to sinking of support you got here minus 54. So minus 37.5 minus 54 is equal to minus 91.5 kilonewton meter. Similarly, find out what is the piston moment at B is equal to piston moment due to UDL plus piston moment due to sinking of support. MB is equal to MB1 plus MB2 is equal to, so MB1 is equal to minus 37.5 and MB2 is equal to plus 54. Minus 37.5 plus 54, so this is equal to plus 16.5 kilonewton meter. So this is the moment here you got, this is your negative anti-clockwise, and here this is MB is your positive, so this is also anti-clockwise, because for piston moment, so right side for negative moment, right side is your clockwise and left side is your anti-clockwise. But here you got the MB is your positive, so here the direction of the MB is your anti-clockwise direction. This is the direction, anti-clockwise. MB direction is your anti-clockwise, and this is MA direction is also anti-clockwise, negative. After getting MA and MB, then you have to find out what is the reaction. Then you have to find out the shear force at different position. Then you can draw the shear force diagram, and also you can draw the bending moment diagram. So first you find out what is the reaction. Reaction at support A, take BA, and reaction at support B, take BB. So first you find out by taking moment about A. So what is the moment? This is the MA anti-clockwise, and here this is the moment anti-clockwise, and due to this UTL, so the moment is your clockwise, and due to this reaction, the moment is anti-clockwise. When you are taking a moment about A, due to this reaction, the moment is anti-clockwise, and this is moment at A anti-clockwise, moment at B anti-clockwise, and due to this load, the moment is clockwise. So anti-clockwise moment is equal to clockwise moment. BA into 5 minus 91.5 minus 16.5 minus 18 into 5 into 2.5 is equal to 0. Then after simplification, so you'll get the reaction at A is equal to 66.6 kilonewton. Then take summation of vertical force is 0. So here this is the vertical reaction at A, this is reaction at B, and this is the downward force. So BA plus BB minus 18 into 5B is equal to 0. And BA plus BB is equal to 18 into 5. So after simplification, because you know BA is equal to 66.6 kilonewton, and here you will get BB is equal to 23.4 kilonewton. So this is the reaction at the end. So this reaction you have to find out by considering the load and the end moments. Then you have to find out what is the shear force at different position. So shear force at B, FB is equal to BB is equal to minus 23.4 kilonewton. Because this is the reaction at B, shear force at FB is equal to minus 23.4 kilonewton. Then shear force at A is equal to minus 23.4 plus what is the load you are present on the beam, 18 into 5 plus 18 into 5. So this is equal to 66.6 kilonewton is equal to A. So this is the shear force at A. Shear force at A is your 66.6 kilonewton and shear force at B minus 23.4 kilonewton. Then find out what is the zero shear force, because this is the shear force diagram. So this is 23.4. This is shear force diagram. This is 23.4 kilonewton negative. And here the shear force, this is 66.6 kilonewton positive. This will go linearly. The shear force diagram will be linear because this is the UDL. So here you have to join this point and this point. So this will go linearly. This is the positive shear force and this is negative. So here you have to find out the zero shear force position. The zero shear force position, you will get the maximum bending moment. So find out, let the shear force be 0 at a distance x from the support A. From the distance x from support A, so the shear force is equal to 0. Find out Fx is equal to Va minus 18 into x. This is the upward force and this is the UDL. Va minus 18 into x. Va minus 18 in x is equal to 0. X is equal to 66.6 by 18 is equal to 3.7 meter. So at a distance 3.7 meter from support A, so you will get the maximum positive moment. So maximum sagging moment or positive moment is equal to 66.6 into 3.7 minus 91.5 minus 18 into 3.7 square by 2 is equal to 31.71 kilonewton meter. As you have to take what is the moment here. Here at a distance 3.7 meter from the support A. So Va into 3.7 minus Ma, then this is due to this one, minus 18 into 3.7 into 3.7 by 2. This one, 18 into 3.7 into 3.7 by 2. This is the moment, both are anti-clockwise, negative, and due to this reaction, here the moment at a distance 3.7, this is positive, clockwise. Maximum sagging moment is equal to 31.71 kilonewton meter. So here the maximum moment 31.71 kilonewton meter. So this is the bending moment diagram. So this is the pre-BMT positive bending moment, and this is the support moment, because here you got the support moment is your negative minus 91.5 kilonewton meter, but MB you got plus 16.5 kilonewton meter. Here you see MA is you got MA you got minus 91.5 kilonewton meter, and MB you got 16.5 kilonewton meter. So this is 91.5. This side is your 91.5 kilonewton meter negative, and this side this is your 16.5 opposite, because this side is your negative, this side is your positive, and this 3 BMT is your positive. So after this portion is your cancel each other. This portion is cancel each other due to positive negative, and this remaining portion positive, and this also positive. This is also positive. Means this is the combined bending moment diagram, or the final bending moment diagram of the fixed beam when the sinking of support takes place. So this portion is your positive portion, and this portion is negative. So the negative moment at A is 91.5 kilonewton meter, and the positive moment or sagging moment at a distance 3.7 meter is 31.71 kilonewton meter. Also you can find out what is the positive moment at the midpoint. Here also you can find out what is the positive, because you know what is the ordinate of the total 3 BMT. This is 56.25 kilonewton meter. If you will deduct this portion, then you will get what is the positive moment or sagging moment at the midpoint of the fixed beam. This also you can find out, because you know already we have discussed in previous classes, because you have to only deduct this portion. So this portion that you can find out, because here you see this is one triangle, this is another triangle. If this side you take x, you take this side is your x, so this side is your I minus x. So x by 91.5 is equal to 5 minus x by 16.5. Then you will get what is the distance x, what is the length this x. So after getting this length, then you have to take two triangle here, because this is one triangle and this is another triangle. Then you can find out what is this ordinate, because you got here this one, this length. By taking these two similar triangle, you got this length. Then what you have to do, because you have to find out the midpoint. So midpoint means from this to this is your 2.5 meter, and you know this length, so you can find out this one. You can find out this length. So after getting this length, by taking the two similar triangle, this is one triangle and this is another triangle, so you get this value. Then after deducting from this total, you will get what is the sagging moment at the midpoint of the fixed beam, because 91.5 divided by this side is equal to this side divided by this side. Then you will get what is the value of this one. Then after deduct from this total, you will get what is the positive moment at the midpoint of the fixed beam. This is all about the fixed bending moment diagram and the shear force diagram. When there is sinking of support takes place, all are clear. When due to the sinking of support, how we will find out the fixed end moment at the end of a fixed beam.